Hello. Welcome back to lesson 4.6. I realize I haven't posted or updated any videos in a while. I apologize. I've been busy procrastinating. Um, that being said, that was partly intentional. I didn't think that these lessons were too complicated. That you needed extra instruction. I mean, if you hopefully looked at the answer key, um, the completed notes, it would be fairly evident what we're doing here. I will go over these lessons in brief, although, like I said, I don't think you guys need too much help on this stuff. I do acknowledge that maybe like somewhere down the line, I think it was 4.8. This lesson might require some finessing, I guess. But apart from that, I think most of these lessons are fairly self-explanatory. But again, we'll go over them in brief just to make sure that you're understanding what the main concepts are and what you have to know. So, use a table of values. So you're just putting in values into y equals 2 to the power of x. So 2 to the power of -1 um, is a negative exponent. So you move the base to the denominator and make it a positive exponent. So that's half. 2 to the power of 0 is 1. 2 to the power of 1 is 2, 4, 8, 16, 32. And we know what happens as we keep going. It keeps increasing. So we have, at -1, we have a kind of, oh, where's half here? It's like somewhere at the bottom, somewhere over there. And we have a 1. So I think this is 10 and this is 5. So that's half in there. 1. And then 1 gets 2. 2 is a 4. 3 is 8. 4 jumps all the way up to 16. 5 goes to 32. And we can see that this graph is going to get bigger and bigger. And I'm sure you've seen this kind of graph before, especially considering the current pandemic situation. The exponential graphs are usually what are used to model pandemic growth and disease spreads in a population. So this means that 2 to the power of x is every time unit. The number of cases approximately doubles or something, which is currently the case. Or actually, I shouldn't say is currently the case because we, I think, have successfully succeeded in flattening the curve, as in this graph no longer looks like an exponential graph, and Canada's graph looks kind of flattened. But if you look at the graph that's probably currently occurring in the United States, or especially New York or the Italy or Spain, you'll see the cases grow at somewhat of this shape, this graph looking shape. So what happens to the value of y as x moves to the right? The value of y doubles every time x moves 1 to the right. It just increases, increases more and more. Draw the horizontal asymptote. Here's your horizontal asymptote. Y equals 0. And we know that no matter what value of x you have, you're never going to have a y value of 0. So even if you have x as negative 1,000 or 10,000, your y value will be 2 to the power of negative 10,000, which is 1 over 2 to the power of 10,000. Now, 2 to the power of 10,000 is an incredibly big number. 1 over that is an incredibly small number. It'd be like 0.0000000 something, but it's not 0, right? It's somewhere really, really close to 0. Domain is just like parabolas. Usually the domain is not restricted. It's just XER. There's no limitations on what x can be. However, you can see here that because I have a horizontal asymptote and no negative side of the graph, obviously the range here is going to be restricted to y greater than 0. It's important to note that there's no equal to sign. It's not greater than or equal to 0. It's just greater than 0 because y equals 0 is the asymptote. Does the graph cross the x-axis? No. Is it increasing or decreasing? Increasing. That just means as you go from left to right, does the graph go up or down? That's basically what that means, right? Hopefully we're familiar with the term increasing. As we read, again, we always read the graph from left to right. Some students get confused over that. Just always read it left to right, right? As you move from left to right, is the y value going up or the y value going down? And we can see here that it's going up as we progress along the graph. So that's that. This is basically kind of the same equation, except instead of 2 to the power of x, it's 5 to the power of x. So here we have 1 over 5, 1, 5, 25, 125, 625, 3125, etc., etc. And if you were to plot this, this would look, I mean, mostly kind of similar to the graph that we had, except it's going to be much more steep. 25 and 125 is already like, I can't even plot that on the 3 is 1 3. Yeah, it's like somewhere all the way. Yeah, it's out of my screen. Somewhere far away. So you can see here that it's pretty steep. The slope of this at this point gets pretty steep. And I apologize for my wonky looking graph, but again, here it's fairly self-explanatory. The same horizontal asymptote, same domain, same range. No, it's an increasing. And again, just because the only thing that changes with the base is the steepness of the graph. So if I had a 10 to the power of x, that would look like even more steep. It would go like, woo, something like that, etc. And if I had I guess 1 to the power of x is just a straight line. So that's not really a graph, but yeah, you get the idea. 4 to the power of x would be less steeper than that. So it would go up slower, and 3 to the power of x, 2 to the power of x, that kind of thing. Those are not accurate values, just to show you that what the base does to the exponential function graph. So, I guess that was the next question. I didn't look ahead. Again, what are the common characteristics that's important? The domain will be the same. The range will be the same as we saw last time. The y-intercept will be the same. And of course, we know that's the y-intercept at x equals to 0, y equals to 1. 1. No matter what the base is, right? 2 to the power of 0 is 1. 5 to the power of 0 is 1. 10 to the power of 0 is 1. So your y-intercept is always 1. Horizontal asymptote is another common characteristic, as we saw in the last page. 7 to the power of x will lie in steepness somewhere between 5 to the power of x and 10 to the power of x. Write a general description of the curve f of x equals b to the power of x. That is just, you're just going to put all these things. So general description, you know that the domain is going to be xer, the range is going to be yer, y greater than 0. It's going to have a horizontal asymptote of y equals to 0, y-intercept of at 0, 1. All these things are general descriptions of this curve. Again, the important thing that's on the answer key to point out here that is only applies for b greater than 1. What does that mean? It only applies for 2, 5, 10, any number that's greater than 1. Because as soon as you have a number that's less than 1, for example, half, 1 over 5, 1 over 10, the easiest way I find to think about this is let's take a look at this in terms of, let's try and write half as what happens when you change 2 to the power of x, because this is half to the power of x, correct? And let's move this 2 back to the numerator. So I'm moving the base, I'm switching the base around. So I'm making this 2 to the power of negative 1 to the power of x. And hopefully we agree that this is the same thing, because if I move the 2 to the numerator, my exponent is going to change its sign. And this is 2 to the power of negative x. So technically what we're doing is we're just putting a negative sign in front of the x, which we know means that we have a vertical reflection Vertical reflection? No, we have a horizontal, whoops. We have a horizontal reflection across the y-axis. Correct? So that's what, if you have a negative in front of the x kind of term, you know that that's what that means. You have a horizontal reflection across the y-axis. And if you wanted to plot values and see that, you would get the same thing. And okay, let's try and horizontally reflect this over the y-axis. So this is the y-axis, and we're reflecting this horizontally across there. So you can see here that this is going to look like somewhat opposite. It's going to have the same, it's going to cross the y-axis at the same point, but then maybe I should have picked a different color for that. Whoops. But hopefully we can see that this is what's happening to the graph. I'm just switching it, I'm just reflecting it over the y-axis, and this is what the graph of half of x corresponds to. Like half of x is going to look somewhat like, I'm exaggerating this, these are not exact values. This is what the graph of half of x is going to look like. 1 over 5x is going to be steeper than that, but again, it's going to have the same y-intercept, the same asymptote. 1 over 10x is going to be even steeper, but again, same y-intercept, same horizontal asymptote, but it's just going to be reflected over the y-axis. So that is the common characteristic there. Again, the same characteristics are the same: y-intercept, domain, range, horizontal asymptote. But of course, you will notice that these graphs are decreasing instead of increasing, because as we move from left to right, we see that these graphs are, I mean, the arrows point in both directions, obviously, but as we move from left to right, these graphs are going down, or they're decreasing in y value. And so therefore, they're decreasing graphs. So 1 over 7 will lie in between 1 over 5 and 1 over 10. So that's where 1 over 7 in terms of steepness. Again, just general stuff. The bigger the number, the more steep it is. Even, I mean, I guess I shouldn't say the bigger the number, because 1 over 10 is technically smaller than 1 over 5. You know what I'm, hopefully you understand what I'm saying. Like this number here, if you convert this into a negative exponent, this is technically 2 to the power of negative x, 5 to the power of negative x, and 10 to the power of negative x, right? And the bigger now the bigger the base, the steeper the graph, just as before. And so yeah, that's basically exponential functions in a nutshell. And of course there are some I wouldn't say exceptions, but some things that you can add on to this. But again, as Mr. Chermoli said extensively, it all comes back to the first unit and the idea of transforming graphs and the idea of like vertically stretching, horizontally compressing, all that you have to know well, because after you know all those things, it's not that hard to do these kinds of graphs. So, okay, basically this column is probably the easiest to fill, because all these have positive exponents automatically. So if you have a number that's greater than 1, like 2 or 3 or 2 or 4, you're going to have a increasing graph. I guess not all the time. Yeah, I guess it depends on the negative sign in front. So we'll go over them step by step. I mean, it's still easy. It's just not as straightforward as you would hope. So okay, how does the y-intercept change? Let's go over what affects the y-intercept. Assuming all you have are powers of x, and we're not going to change that. It's just going to be power of x, power of x. The things that affect the y-intercept are the a value, because that's what we're changing compared to our previous cases. We're just adding a values when in some of these cases. So the a value changes the y-intercept by simply multiplying into it. So normally we know that the y-intercept is 1. Here we have an a value of 3, so our new y-intercept is going to be 3. Here our a value is 1, so y-intercept is 1. A value is 4, y-intercept is 4 times 1. A value is 2, y-intercept is 2, a value is -3, -2, -3 times 1. So y-intercept stuff is fairly straightforward, hopefully. In terms of whether the graph is increasing or decreasing, there's two things that affect that. One is your base. So if your base, so check your base. If it's greater than 1, that means it's increasing. If it's lesser than 1, that means it's decreasing. However, you also have to make sure to check your a value. If your a value is negative, you have to flip that, because what happens if your a value is negative? And normally, an increasing function, which looks like this, would now be flipped vertically over the x-axis, right? So my graph is going to look like this now, and this is in fact decreasing, because if I read it from left to right, my y value is going down. And likewise, if I flip this function, it's going to look like this, which is also increasing as I move from left to right. So if my a value is negative, I have to kind of flip these conventions that I know. And let me erase this so that we have room to write. There. So a value is greater than 1. B is greater than 1. A is positive. That's increasing. The b is fractional, so this is decreasing. Fractional, decreasing. Greater than 1, increasing. Greater than 1, but there's a negative sign. And so therefore, it was increasing, but because of the negative a value, I switched that to decreasing. Whole number, so it was increasing, but because of the negative sign in the a value, I switch it to decreasing. This is fractional, so I would be decreasing, but there's a negative sign in the a value, so I flip that to increasing. And hopefully, again, we saw that how that worked, because the negative in the a value makes for a vertical reflection across the x-axis, right? So I flip it, and therefore my increasing, decreasing changes. And here it's just basically, I think, just plugging in some points. And I mean, usually you just go by whatever the base is. So if we're putting in 1, I would have 2 to the power of 1, 2, but I have to multiply that by 3, so it's 6. And here I have -1. Be careful here. Don't rush to substitute in. Hopefully we see that we're getting 3 over 2 and not 1 over 6. So it's not always just the reciprocal, because I'm just multiplying by 3. This is 1 over 3, -1, +3. Here I have the same idea. So I flip that, but multiply it by 4, so +12. Is that 3? Yeah, 1. So 3 to the power of 1 is 3, times 2 is 6. 3 to the power of -1 is 1 over 3, times 2 is 2 over 3. Did I flip something? No, that's correct, right? Yeah, I think there might. Watch out! I'm looking at the answer key, and I think there might be something. Oh no, it's just the answer key just wrote that in a different order, so they put the -1 first. Yeah, again, doesn't really matter what order you're writing this in. Again, this is just substituting these values into the equation, and yeah. I don't know why he chose to flip that. It's interesting, but that's fine. And again, you can graph, I guess, all these functions. Again, I'm not actually going to graph them because again, you'll see that there's, I'll go over this again once again. There's four distinct shapes, right? So if you look at your A and B values, first the case you have where your B value is greater than 1, so 2 to the power of x, and your A value is positive. So just a graph of 2 to the power of x, you have something that looks like this. And the y-intercept is, of course, in this case 1, but it could go up or down depending on your A value. So if your A value is 2, your y-intercept is 2, etc., etc. Next is the case where we have, we'll just do the negative here first. So we have the case where our b is still greater than 1, like 2 to the power of x, but our a value here is negative. So example, negative 2 to the power of x. And this graph looks like this, again, with the y-intercept being the negative of whatever your a value is. If it's negative 2 to the power of x, that's a y-intercept of negative 1. If it's negative 3 times 2 to the power of x, that's a y-intercept of negative 3. If it's negative 5 times 2 to the power of x, that's a y-intercept of negative 5. But this is what your graph will look like. I just flipped that. And the other two graphs are, of course, if b is lesser than 1. So if I have a fractional, 1 over 5 to the power of x, we saw that the graph looks like this. With, again, this is the case where a value is positive. Again, y-intercept of positive 1, unless my a value is not 1, in which case it's a y-intercept of whatever my a value is. And, of course, the case where my a value is negative, and so I'm going to reflect that over the y-axis, over the x-axis, and get a graph that looks like this. So again, I just flipped this over the x-axis. Again, be careful when the y-axis reflection is when I change my b value. My x-axis reflection is when I change my a value. Kind of similar to like your a value and k value in our standard function in unit 1, right? So I'm going to leave you to graph again. The y-intercept is just, as long as you plot the y-intercept correctly, you basically have this graph. Don't worry too much about exact points on this graph. I'm just looking for a rough shape. I'm not really sure how the assessments are gonna work, but generally teachers just look for the rough shape. So as long as you have the y-intercept marked properly, you have maybe like what your value is, like this point labeled. You have this point labeled. It doesn't really matter where these points are and if they're not like exactly where they're supposed to be, as long as you get these 3 points in the general shape correct, and it looks like you have a asymptote here, which it doesn't always look for me, but that's kind of important. As long as you have that asymptote clearly marked, that's basically what we're looking for. And 3 points, the 3 points around here. That's basically it. Of course, there is another thing that can change the y-intercept, is if you move the graph, of course, up, down, or in fact left or right. So that comes into cases where you have 2 raised to x plus 3. This is, you've moved this graph vertically up 3 units, right? So my y-intercept is going to change by plus 3. We're not obviously going to talk about horizontal shifts, because that looks like this, and that's kind of funny, and it could be just moved over, I guess, to the a value and changed there. So again, we're not going to do cases like that. Just I see that there is a note in the answer key, just to be careful that if you do have a plus c, that gets included in your calculation of y-intercept. So for example, again, 2 times 5 to the power of x plus 3. Your new y-intercept would be 2 times 1, because normally it's 1. If it's this, the y-intercept is 1. Your new y-intercept is going to be 2 times 1 plus 3. So that's 5. This is going to be your y-intercept. So as soon as you mark your y-intercept, you can kind of sub in 1 and negative 1 here, find your 2 points, and then just draw the graph that looks like that. Again, hopefully this is not too confusing. Go over some of this review, make sure you're understanding what's going on. If you have any questions, of course, you can ask, but yeah, hopefully we'll see that this is not too complicated stuff. And I am in fact just going to continue with the transformations, just because it links very well to the previous lesson, and I don't want to break the flow. Again, in terms of transformation, some of this we've already gone over, but we're just going to look at it in a bit more detail. So okay, again, looking at the general transformed function f of x is equal to a I guess this is the general form that we're used to seeing from Unit 1. And again, just a brief consideration of what things are going to be affected by what. So again, the horizontal asymptote is basically only affected by c. So this c contributes entirely to the horizontal asymptote. And that's because, again, normally we know the horizontal asymptote is y equals 0. If I move the graph up or down, that just means my horizontal asymptote is moving up or down by the same factor of c. So horizontal asymptote here is going to be -6, y equals +4, and of course y equals 0 because there's no c value here, right? There's no c value, so that's just the horizontal asymptote as normal, y equals 0. All right, we've already talked about how to establish the y-intercept. It's the a value and the c value that contribute to our y-intercept, right? So it's a plus c. So here we have a 3 minus 6, so -3 is our y-intercept. -2 plus 4, which is +2, is our y-intercept. And here we have a 1 plus 0, which is just 1. Again, this is just a normal y-intercept because I have no, my a value is 1, +1, and my c value is 0. And there's no c value, so that's my regular y-intercept. We also talked about how to find whether something's increasing or decreasing. Again, I have a b that's greater than 1, positive a value, that's increasing. A fractional b value, so it would be decreasing, except my a value is negative. So this is also increasing because my graph looks like this. Here my graph looks like this. It's always good to draw a rough sketch if you can. And here, this is an interesting case because I have a negative sign in the exponent. And very important to note, again, you should be able to look at this in either form, but if you want to convert that, remove the negative value from the exponent. So what is that if you remove the negative value? Again, I'm moving my base to the denominator and making this a positive exponent. So we'll see here that this is actually a fractional base, and so this is a decreasing function, which looks like this. And that's that. The domain for these things is always XER. There's never any restrictions on the domain for a exponential graph. I guess I should write this in some base to the power of kx minus d. Okay, this probably looks better. B just being here any base, it doesn't really matter what base you have. But this is the general form of the graph. Of course, the f of x being the exponential function. Oh yeah. Again, we won't do horizontal translations for now. We're just gonna not do those. So yeah. The range, of course, is entirely dependent on our horizontal asymptote because, of course, the y value cannot go below the horizontal asymptote. These are not like reciprocal functions where you have like weird two kind of two different curves as just a single curve. For your graph, it's continuous, and therefore your horizontal asymptote being -6. You do have to be careful whether it's above or below -6, and I'll show you what I mean. So here's where the horizontal asymptote is, right? So y is greater than -6. But in this case, when it's a increasing function this way, if you have your horizontal asymptote here, it's actually y is lesser than +4, right? So that's going to be our horizontal. So it's not this. You have to be careful about the sign. It doesn't really depend on whether it's increasing or decreasing. It more so depends on whether you have a b value of positive or fractional. Oh, sorry, b value of a whole number or a fractional b value. So here we have that's your y asymptote, so greater than 0. And again, it's always useful to have this rough sketch in your head based on these kinds of these four scenarios. As long as you know a rough sketch of what you're drawing, it's very easy to come up with the range. Hopefully we can see that. And again, just in terms of graphing, I'm only looking for, so if I were to graph, I'll just show you how to graph A, for example. Again, hopefully we're aware of the general shape. So first you're going to mark your y-intercept of -3. That's somewhere over here, I think. I would also mark my horizontal asymptote, so that's important to mark. Get over here. And once you have these things, really, like, I would also put in x equals 1, maybe. 4 to the power of 1 is 4 times 3 minus 6 is 6. So that's easy to put in. But realistically, you only need like 2 points. You could sub in -1 as well to get like your value that's over here, but that's a fraction of value. You're not going to be able to plot that point exactly anyway, so I just eyeball it and kind of plot your graph. Again, very important is your horizontal asymptote. Your y-intercept is important to have, and maybe 1 point just to see how steep the initial part is, and that's basically it. That's all you really have to plot in terms of graphing. So again, for part B, if I were to plot that graph over here, my y-intercept I would put +2, so I'd mark that point, and my horizontal asymptote at 4. And again, I generally know I'm just going to find my value for -1 because that's the easy value to find. So -2 times, if I put a -1 here, that's 3. So that's basically -6 plus 4 is -2. So -1, -2, that's my point. And again, as long as you know, like in general, the shape of your graph, and you know it's going to look somewhat like this, as long as you, again, that's a horrible graph, it didn't go through any of my points, but as long as you have your y-intercept in 1 point and a good horizontal asymptote, that's basically all you need to do to graph it. So again, hopefully we'll see that this is normal-ish. Here it's important kind of because this is the only one where you have a different k value. And again, what this does is it horizontally stretches or compresses your graph, right? So this is almost like basically changing your b value. Because, for example, like I would just do a kind of 2x, and I'm going to kind of do some exponent. So I'm going to reverse, the power of the power rule. This was a multiplication. And 1/2 to the power of 2 is 1/4 to the power of x, right? So this is basically just changing my base, kind of. So I'm just going to make it, my graph is either going to get steeper or less steeper, depending on that. But in terms of the key characteristics of the graph, it's not going to change. It's not going to change the domain, the range, the horizontal asymptote, the y-intercept. None of that's going to change because of this 2. It's just going to be less or more steep. So that's basically it. So as long as you have a good, y-intercept, horizontal asymptote, your graph is going the right way, which is in fact this way, this way. And so you can just plot 1 point maybe. Let's put in -1 in here. So I have 2 to the power of 2, which is 4. So -1 corresponds to 4. So I guess we can even put in -2, and we know that will correspond to 16, I guess. So my graph will get steeper. What a horrible graph. But yeah, you get the idea. Just in terms of how steep the graph should look. And that was our lesson on graphing exponential functions. Again, I do realize that I rushed through that a little bit, but hopefully we're just, as long as we're good with this stuff and how to fill in this table, know how to find, like a horizontal asymptote is just based on c value. Y-intercept is a plus c value. Increase and decreasing, you have to look at the combination of the base, whether it's a whole number or fractional, bigger than 1 or greater than 1 or less than 1. You have to look at your a value, whether that's positive or negative. To flip that, domain's always the same. Range depends on your horizontal asymptote plus the general shape of the graph to see whether it's above your horizontal asymptote or below your horizontal asymptote. So just knowing these things, that's basically all you need to understand here. And yeah, that's basically it. All right. So I will see you all in the next lesson. Until then, peace out.